My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 274. In this lecture, we will try to understand decision surfaces for K nearest neighborhood algorithm. How to pick here one must understand an important concept: how to pick the right k. In order to understand how to pick right k, first we will try to understand decision surfaces. Till now we have been saying k equal to 3, k equal to 5, k equal to 7, so on, whatever it is, but we never said how to pick the right k. So k in KNN is often referred to as hyperparameter. This k is known as hyperparameter. Just recall my lecture number 179. In this lecture, I discussed about linear regression demonstration. In that lecture, we were saying that y equal to b0 plus b1x. This b0, b1 are known as parameters, whereas k in KNN is known as hyperparameters. I will differentiate between parameters and hyperparameters in my future lectures. Just remember for now that k is a hyperparameter in KNN. Now, how do we determine k? That's important. How to pick the right k? What is the right way to determine k? And how things change when k changes? What happens when k equal to 1? What happens when k equal to 3? What happens when k equal to 5? We will try to understand geometrically. Understand what happens geometrically. Understand what happens geometrically when k equal to 1, when k equal to 3, when k equal to 5. If you got a geometrical understanding, our intuition of k nearest neighborhood improves dramatically. Before we go and understand what happens as k changes, let me take a simple data set. If we speak strictly, let's assume this is a data set. This is also a data set. Let's assume these are exactly same data set. Here blues are, let me write, yes, here one must understand this. Blues are positive points, positive data points, and reds are negative points or negative data points. One thing you notice here, all of these, just see this one, all of these are negative points, that is red points, and there is one positive point, that is blue point. There is one positive point. I just have one positive point in the region of negative points, in the region of red points. Means negative points are red points. There is one negative point. Just see, this is positive point region, this is blue points region, in which you have one negative point. There is one negative point in the region of positive points, except that there is a very nice data set. If I ask a 10-year-old kid to draw a line or a curve to separate this, he might likely to draw like this. He might likely to draw like this, isn't it? Otherwise, let me redraw it like this. How a kid can draw it? Let me say like this, isn't it? What happens? Everything left side of it means this side. Everything left side of this particular curve, everything left side of it is negative points, isn't it? Red points, isn't it? And right side of it, what about right side of it? Right side of it is positive points, isn't it? Yes, everything, let me repeat, everything left side of it is negative points, right side of it is positive point. This is one way to draw a curve, isn't it? This is one way to draw a curve to separate these two. There is other way to draw the curve that separates, because if I draw like this, what happens? Let me repeat. If I draw like this, there is one positive point. Just see. There is one positive point in negative side. Red point region means negative side. There is one positive point on negative side and a negative point. Red point means negative point and a negative point on positive side. 2 points are classified. 2 points are classified. 2 points are classified. 2 points are classified. How they classified? Is it not simple and straightforward? 2 points are classified incorrectly. Incorrectly, isn't it? By this curve. Which curve? By this curve. By this curve. Somebody who gives more important to make no errors. Somebody who gives more important to make no errors. He could say, let's not draw this line. Let's not draw this curve, isn't it? Like this. Let's draw a curve like this. Let me say like this. How can I say? Just see. If I draw like this, let me say like this. Yes. What happens? Yes, let me say like this. Yes, I will repeat. Somebody who gives more important to make no errors, he could say, let's not draw this particular curve. Because of this particular curve, we are making 2 misclassifications. Now we can say, therefore, he may draw this curve like this. What happens? Now we can say everything on right side of this curve. Just see, everything on right side of this particular curve is positive points. Everything left side of this curve is negative points. Isn't it? If someone is not interested to make no errors, he might draw this curve like this. Isn't it? So when I have a curve, this case 1, let me say this is case 1. Let me say this is case 2. Case 1, when I have curve like case 1, what happens? My case 1 curve makes 2 errors. This is one error, this is another error, isn't it? While case 2 curve, this is my case 2 curve, while case 2 curve here makes no errors, but my case 1 curve is also very smooth. This curve is smooth curve, very smooth curve, very smooth curve, isn't it? It is not jagged. This curve is not jogged. Not jagged. While case 2 curve has all sorts of twists, and this curve has all sorts of twists, isn't it? Twists and turns, twists and twists and turns, which is also known as it is non-smooth curve, which is known as non-smooth curve, isn't it? It's a non-smooth curve. Both of these curves are separating positive points and negative points. Both of them are trying to do that, but they are separating. But case 1 curve is much more smoother than case 2 curve. These curves that separate positive points from negative points and vice versa, such curves are called decision surfaces. This curve is decision surface. This curve is also known as decision surfaces. You might wonder why are they called surfaces, not simple decision curves? Because what we are specify here in this is what we are seeing here. Otherwise, let me say what we are seeing here. This is 2D example. Is it not 2D? This is 2D. This is 2D example, isn't it? We are seeing 2D example. What happens when 3D? When 3D, in 2D I can say it is a curve. In 2D it is a curve. In 3D what happens? In 3D basically it is a surface. In 3D basically it is a surface. In ND, in n-dimensional space, it becomes hypersurface. Hyper surface. In ND it becomes hypersurface. It's called decision surface. This surface is known as, this is decision surface, isn't it? It decides why they are calling it as decision surface. It decides whether something is positive or negative depending on which side of the curve it lies. So such curves in machine learning are called decision surfaces. What we are seeing here is 2D. If this data is n-dimensional space, it's no more simple curve like this. It is no more simple curve like this. No more simple curve like this. It is a surface or hypersurface. The case 1 and case 2. This is my case 1. This is my case 2. This is case 2. This is my case 1. Isn't it? The case 1 and case 2 are called decision surfaces, and decision surfaces are helps us in understanding what happens as k increases. Decision surfaces, very interesting geometric concept that we will use throughout this lecture series, and especially in this case to understand what happens when k equal to 1, what happens when k equal to 3, what happens when k equal to 5. Just time being, go through this concept. In my next lecture, I will continue my discussion on how to pick right k. Thank you very much.